Unit 8, Chemical Bonding, pages 187 to 191, exceptions to the octet. So the first type of exception is an odd number of total valence electron, also known as radicals. When the total valence electrons is an odd number, there's no way to satisfy each atom with an octet of electrons. These molecules are called radicals. They're very reactive species, and some are responsible for cell damage in the human body. Here are some examples of radicals. So nitrogen has 5 valence plus oxygen has 6, and that's going to give us 11 valence. Oxygen has 6 plus hydrogen has 1, which gives you 7 valence. Chlorine has 7 plus oxygen has 6 times 2, which gives us 19 total valence. Using formal charges in Lewis structures of radicals, when an odd number of valence electrons, one of the atoms in the Lewis structure will not have an octet and will be missing an electron, but which atom will be missing the electron? So you can use formal charges to decide which atom should be the better choice. Here you have nitrogen monoxide, and you have a formal charge of -1 on this nitrogen and a +1 on the oxygen. And then in this other scenario, placing the radical on the other atom, you have a 0 formal charge on nitrogen and a 0 formal charge on oxygen. This is going to be the better option because both of them have a formal charge of 0, which is more ideal. The formal charges for this radical indicate that structure B will more likely be since the formal charges are 0 for both atoms. The second violation of the octet rule would be if there are less electrons than an octet. There are certain atoms that will never make it to an octet. Boron cannot have an octet in BF3. Do not be tempted to use non-bonding electrons on the fluorine to make a double bond. Fluorine is too electronegative to make a double bond. The atoms hydrogen, helium, lithium, beryllium, and boron will have less than an octet of electrons. Here's an example of a molecule. This is BF3, and notice it only has 3 bonds. 1, 2, 3. And so it can only have 6 electrons maximum. On your note card at the end of the video, I'll have some other examples that'll have less than an octet. More electrons in an octet, also known as exceeding the octet rule. The elements in the third row and below in the periodic table can have more than 8 electrons in the Lewis structure. These elements use their d orbitals for making covalent bonds and storing non-bonding electrons. This is called an expanded valence. So, for example, you have phosphorus and has 5 bonds, 5 chlorine atoms surrounding it, which gives it 2, 4, 6, 8, 10. So it has more than an octet because it has 10 electrons shared around it. These are the elements that can have an expanded valence. Note that expanded valence occurs more often with electronegative atoms, oxygen, fluorine, chlorine, attached to one of the atoms below as a central atom. So these are typical elements that'll be central atoms that have an expanded octet. So in summary, multiple bonds result from molecules with too few electrons, in which we do not have an octet, and so we have to shift down electrons to make multiple bonds so that we can achieve octets for all atoms involved in the bonding. If you have more than an octet result from too many valence electrons, for example, here the xenon difluoride was going to end up having 2, 4, 6, 8, 10 electrons around the xenon, and that's allowed even though it's an octet of the violation rule. It's called an expanded octet, and this is one of the elements that's capable of harboring one. Charges on the atoms in a molecular compound. There are several ways to determine which atoms in a molecule, if any, have charges. Investigate the formal charges. Compare the electronegativities of atoms in each bond. If there's a difference in electronegativity more than 0.4, the higher the electronegativity atom will have a partial negative charge. The higher electronegativity atom has a stronger pull on electrons. So exercise 8.46. Determine which atoms are charged or have partial charges. So the electronegativity values for each of these are as follows. 3.0 for nitrogen, 2.1 for hydrogen, 2.5 for carbon. So if we want to just analyze one nitrogen and hydrogen bond, the difference between them is equal to 0.9, which is going to fall in the polar covalent range based on our scale that we use. Now we can look at a carbon-hydrogen bond, and remember hydrogen is 2.1. The difference here is 0.4, which is in the non-polar covalent range. And then we can look at the carbon and nitrogen bond, which has a difference of 0.5, which also falls in the polar covalent range. So whenever it's polar covalent, the more electronegative element, in this case the nitrogen, is going to have a partial negative charge, while the carbon is going to have a partial positive charge. And then between the carbon and the hydrogen, it's nonpolar covalent, so neither of them is going to have a charge. And then between hydrogen and nitrogen, you have a difference of 0.9. So again, the nitrogen will be partial negative and the hydrogen will be partially positive. In the molecule on the left, NH2CH3, all of the atoms have a formal charge of 0. The atom with the highest electronegativity is nitrogen with a 3.0. Hydrogen has a 2.1, carbon a 2.5, so all of the bonds of nitrogen will have an electronegativity difference of greater than 0.4. These are polar bonds with partial charges. The higher the electronegativity, the higher electronegative nitrogen atom will have the partial negative charge, and all atoms attached to nitrogen will have the partial positive charges. For the molecule on the right, NH3CH3, the nitrogen atom has a formal charge of +1. All the other atoms have a 0 formal charge. The molecule is really NH3CH3 with an overall +1 charge, with the positive charge located on the nitrogen atom specifically. Here is your note card for this section. There are 3 ways to violate the octet rule. Beryllium will only make 2 bonds and have 4 valence electrons maximum. Boron only makes 3 bonds, and so 6 electrons max. You can exceed the octet. Usually it's an element that's got an atomic number of 15 or higher, and they can potentially have more than an octet around them, and that's considered a violation of the octet rule. And then radicals, when you have a total valence that's equal to an odd number. Partial charges happen when you have polar covalent compounds. The more electronegative element is going to have a partial negative charge, and the less electronegative element will have a partial positive charge.